Hello, good people. Welcome to video number 3. We are applying the integral test for convergence or divergence of infinite series. I'd like to do number 5 and number 6 with you, and then we'll think about number 7 in this video. But for number 5, can I convert this into an integral from 1 to infinity? I call it a parallel function, which really means it's just the same formula here, except x's instead of n's, right? Is this decreasing, positive, and continuous on the interval from 1 to infinity? And then number 2, is it even integrable, right? Can I take the antiderivative? And so I believe it is decreasing. And I say that because if I take the limit of this, it's going to go to 0. I believe it is positive because I'm only putting in numbers, substituting x values from 1 to infinity. And since I'm squaring on the bottom, it's just going to make them positive. And is it continuous? Well, the only thing that would make this discontinuous would be if the denominator would equal 0, because then I would be dividing by 0, but nothing makes a denominator equal to 0. So this function is positive, is continuous, and it is decreasing. Check. So now how do I take the antiderivative? Is it even possible to take the integral of this? It is, if we use u substitution. So let u equals x squared plus 1. That means the derivative of that would be 2x dx. Well, I don't have a 2x dx. I have a u squared plus 1, right? So this part is here, but what I don't have is this part yet. However, if I multiply this x by 2 and I compensate that with a 1/2 multiplication outside of the integral, now I have my 2x dx. And so this is going to become 1/2 integral of, I'm going to go ahead and change the limits here. And by the way, as I change the limits of integration, I'm also introducing a limit as b approaches infinity, because this is an integral that involves infinity. So let's see, 1 substituted in for the x value would give me a u value of 2, and infinity, or big numbers, substituted and squared plus 1 is just going to be infinity. So this is still a b value that's approaching infinity. And then I can do the substitution here. So this would be du over u. Is that correct? I believe so. So therefore, I recognize this. This is a natural log. So really, we're going to take the limit as b approaches infinity of 1/2 times the natural log of the absolute value of u from 2 to b. I don't need to go back into the world of x's since I switched my limits of integration. I don't need to write this as the natural log of x squared plus 1 because I already switched these. So I can just do the substitution for the fundamental theorem of calculus, which says whenever I'm taking an integral, take the antiderivative, and then substitute the top value minus substitute the bottom value. Now, as I do this and I substitute big values into the natural log, this is going to go to infinity minus, it really doesn't matter what this is because this is an insignificant constant. This whole thing is going to diverge. And if this diverges, then the original series diverges by the integral test. And we're done with that piece. All right. So the integral test, again, as long as I have a function that is positive, that is continuous, that is decreasing on the interval, then and is also integrable, I can take the integral of that. Find the antiderivative and solve it. Then I can do an improper integral and figure that out. Whatever the improper integral does, that's what the original infinite series does. Be careful. They behave the same way. However, if the integral converges, it doesn't necessarily mean that the infinite series converges to that same value. Okay, number 6. I am taking the infinite series from 1 to infinity of n to the k minus 1 over n to the k plus 2, where k is some positive integer. I don't know what it is, but it's some positive integer. Assume the series meets the criteria for the integral test. So number 6, They're saying definitely use the integral test. Okay, so that means I need to rewrite this as the integral from 1 to infinity of x to the k minus 1 over x to the k and then plus 2. Okay, well, it's an improper integral, so I know it's going to involve a limit as b approaches infinity from 1 to b. But as I look at this, well, how am I going to take the antiderivative of that? Well, if I set this equal to u, then du is going to be, how do I take the derivative of a power function, multiply the exponent in front, and then times x to the power of the exponent minus 1. And then the derivative of 2 is 0. So this is it. Hey, that's almost what I have, except I don't have a k, but I can compensate that with the 1 over k here. Okay, so let's go ahead and change it. And again, as I change it, I'm going to go ahead and also change my limits of integration here. If I substitute 1 into the green formula to figure out my u value, it's just going to come up with 3. Remember, k is a positive integer, so it's some positive whole number. That means when I substitute 1 to any positive whole number is 1, plus 2 is 3. And then if I substitute a big value and take it to the kth power plus 2, I'm just going to get an even bigger value. So this is still going to infinity. So I got that done. Let me change this color to just regular a black marker here. I still have this 1 over k. And now this, oh, and I'm sorry, I forgot to originally put a dx here. So now I have all of this would be du, and then this part is my u, so that's in the denominator, and once again I have this natural log. Awesome, the antiderivative of the natural log. So we're going to take the limit as b approaches infinity of the antiderivative of this, which would be natural log of the absolute value of u. We're going to evaluate that at 3 and at b, not in that order. So this will be the limit as b approaches infinity. And again, as I'm writing this, you might be thinking, why is he continuing to write it all down? Do I have to write the limit as b approaches infinity every time? I do, because when you don't, that causes what's known as a linkage error. Like it was this at the beginning and now it's this at the end, and where did the limit come from, or where did the limit go? Like, you need to show the grader that you understand that this is what you're doing. Not only that you understand, but show them that this is what you're doing. We're taking the limit of this integral. I'm still taking the limit of this antiderivative, and I'm going to take the limit of this expression. And when I do, oh, this is going to be infinity minus 1 over k natural log of 3. So obviously this diverges, and therefore the original series diverges by the integral test. So the moral of the story is, please, please, please show your work. It's usually helpful if you go from step 1, step 2, step 3, step 4, and show I guess make it explicit what your process is. And I used arrows here, I used equals here, I used another equal sign here, and then that got me to this part. Both of these produced a divergent infinite series. Now, when I look at number 7, and this will be the last one, although number 8 looks kind of fun. We'll come back to it maybe in another video. Number 7, let f be a positive, continuous, and decreasing function. All right, so I know I have the conditions met. If the integral from 1 to infinity of f of x dx equals 4, which of the following statements about the series sigma from n to infinity of f of n must be true? Well, this function is the function here, and it converges, or it converged to 4, so that means this converges. Be careful. It doesn't converge to 4, but it converges to a number. So I know A cannot be the answer. The infinite series does not converge to 0. It doesn't equal 0. And D cannot be the answer, because this tells me that the infinite series diverges. So it's either C or B. And so I notice they both have the fact that it converges. But then the second piece says, and the value is less than 4, or the value of the sum is greater than 4. Well, how do I know? And this is where one of the reasons why we talked about how the proof, I guess, of the integral test, if I'm starting at n equals 1, remember the example that we did. If we're starting at n equals 1 on both the integral and the sigma, that means we're drawing a rectangle, a left-sided rectangle, and it's an overestimate. So that means that this not power series, this infinite series must be greater than the area under the curve. And if the area under the curve is 4, then this infinite series must be greater than 4. And my answer, therefore, is B. If you have questions about number 7, bring them to class because we can talk about that for sure. And then finally, I'm not going to do number 9, but we will look at number 8. Explain why the integral test does not apply for this series. And the series is e to the x sine x, and it's starting from 1 to infinity. Why doesn't it work? So I graphed it. Well, here, let me go back. This is what I put into my calculator. Let me do a zoom 6, and I get this. In a standard window, I see this, and I already noticed some things that are failing here. One of the things that's failing is that it's not all positive, right? There's some negative parts. So right there, it doesn't meet the conditions. It doesn't meet the criteria. We are done. Also, I'm starting at x equals 1. So if I'm starting at x equals 1, is it decreasing? Well, no, it goes up and then it goes down. Oh, but then it goes up again. So it's oscillating. And as it's oscillating, it's also getting bigger and bigger and bigger. So the moral of the story is this is not an applicable series with an applicable function. And I can say because f of x equals e to the x sine x is not decreasing and is not positive on the interval from 1 to infinity. Right? We saw it go up and then it went down. So it's not always decreasing. And we saw parts that were positive, but we saw parts that were negative. So it's not always positive. So both of those conditions fail, and therefore it does not apply for this. I cannot use the integral test for this infinite series. All right, so the moral of the story is if you can find a function that is decreasing, positive, and continuous, and that is you can do the integral of that function, then you can use the integral test to determine whether the infinite series is convergent or divergent.